Thank you. Most importantly, we're trying to place in the top 25% overall and top 5 in 30K COTS at Spaceport America Cup. The diagram that you see in front of you is a visual representation of our team structure for this year. Randy Merrick, our AAA flyer of record, as well as our mentor. Dr. Suskan, who is our advisor. So nice to see all of you and meet all of you. My name is Josefina Arguello. I am the project manager of this year. And I work alongside my colleague and peer, Ravi Desai, who is the chief engineer. All of the co-leads that you see, all of the names that you see in front of you, you will be meeting them as they present during this presentation. Shasta 6.
Well, hello, everyone. As Joe mentioned, my name is Ravi Desai, and I'm this year's chief engineer. And now I'll be talking to you more specifically about this year's mission. So I'll start off by mentioning some of the goals of this critical design review. Firstly, and most importantly, we want to receive feedback from alumni, mentors, and professors. This has been a staple of our presentations in the past, and we hope to continue this and really listen to the valuable feedback that everyone has to offer. We also want to demonstrate our competency of design and the progress that we've made since the PDR in order to move forward with our project. And lastly, we want to demonstrate further mitigation of risk from our preliminary design review. We're also attempting a new presentation style this year. In the past, our presentations have notoriously been a few hours long, so we're aiming to cut that to between 30 to 45 minutes tonight. So the current status of Shasta the Sixth. We estimate that we are roughly 65% of the way through our project. We will have all items manufactured, and we'll talk more about that throughout our slides by the end of May, where we deem the project to be 90% complete. And next month's efforts, or in the month of April, will go to implementing any changes and the feedback that we received tonight. Now, a little bit more about what that timeline looks like. So we've allocated a lot of time for our testing to get completed. We also have a media and logistics team this year to help us tackle that spaceport video. April 6th, tonight is our critical design review. And our third interim progress update will be getting started on in the coming weeks, as that's due on April 21st. You'll see manufacturing completed by the end of May, along with those pre-flight checklists. We hope to begin assembly and dry runs, just really practicing that as soon as manufacturing is done, all the way up until the Spaceport America Cup. And we have the technical report on our radar. We have started it, and we plan to finish it around May 1st. So we have around 10 days of buffer so we can get some feedback from any alumni and mentors. Now, next is our budget. So on the left-hand side of the column, you can see our initial budget that we set out for the year. We estimated to spend around $10,800. On the right-hand side of that, you can see the money that we've spent so far and each sub-team's breakdown. We do have a VRBO booked and ready to go in Las Cruces for Spaceport, and that's the part of the $550 that we paid for competition already. Perhaps most importantly on this slide, I want to direct your attention to the amount needed column. The sub-teams, we project that we need a little bit around $500 left to finish spending for any other materials or manufacturing items that we may need. And we're estimating around $5,000 needed for competition in total, bringing us to around $5,500 total needed. Our current balance in our bank account is just under $1,900. So that difference of around $2,500 to $3,000 is really what we're looking for. Our fundraising plan includes events such as Coachella through AIAA, different donations from very generous people such as yourselves, bake sales that we've been continuing to hold throughout the past year, and any sponsorships that we're able to get a hold of throughout or from our AIAA officer team. So now we'll be getting into more of the technical information regarding Shasta, and we'll start off with our analysis team and one of our analysis co-leads, Ariba.
Hi, everyone. My name is Ariba. I am a senior this year studying biotechnology, and I am one of the two analysis co-leads. So the main purpose of analysis this semester was to monitor all the flight simulation files, as well as keep the rocket design up to date with all like the weight changes and any other changes that came to play during manufacturing. So I do want to give you guys a quick overview of the design of Shasta 6. So Shasta 6 is nearly 10.5 feet long and has a 4-inch diameter, is made out of the material G12 fiberglass. It has a 5-to-1 tangent ogive nose cone, which is 19 inches. It has an upper frame of 46 inches and a lower frame of 60 inches. It has a wet mass of 69.3 pounds, as well as a stability of 1.95 calibers. So diving into like the upper airframe, you can see that we have a recovery. The recovery bay is 12 inches when starting from like the nose cone shoulder all the way up to the recovery bulkhead. The recovery will be housing all of the stacked components of the drogue, the shock waves, the main parachute, more shock waves, and then other miscellaneous components such as the fire blanket or the quick links. One thing that is different this year is that due to the smaller space in the rocket, due to the 4-inch diameter, we did separate the recovery and avionics bays into 2 separate bulkheads instead of 1 main bulkhead, which was done in previous years. Because of that, we do have a space between recovery and avionics. That space right there, that space between recovery and avionics will be where our CO2 cartridge will be, which will be used for our ejection system. So the avionics bay, which you see, is 14 inches in length and has about 2 pounds. And directly below that is our payload bay, which is 14 inches as it bleeds into the lower airframe and weighs 8.8 pounds. Right here, the black dotted thing right there, you can see is the motor retention system as well as the motor itself. And then finally, we do have our fins, which are a trapezoidal shape. It is made out of carbon fiber and has a honeycomb center, but our structures lead Brandon will cover that a little bit later. As for our flight simulations, we use 3 flight simulators. We use the Open Rocket, Rosero 2, and RockSim version 10.5. However, the most accurate is RockSim Pro because it integrates the coefficient of drag data taken from Rosero into RockSim. And big shout out to Randy for helping us out there. Thank you so much.
Aerodynamic data to these, and that's plugged into Rocketry.
Okay. Okay, well, thank you for that. So as you can see here, our final expectations for the flight are shown in green. We expect an apogee of around 35,593 feet, a max velocity of 181 Mach, and a max acceleration of 24.74 G, and a stability of 1.82 calibers. Thank you.
Next up, we'll have Scott talking about propulsion and the motor being used for Shasta.
All right, good evening. It's pretty simple here. So this year we are opting to reuse the Cicerone 03400 we used it with Zenith because it meets all the performance requirements we need, and it also saves us the cost of buying a new casing. Our advisor, Randy Merrick, inspected and approved the casing for reflight. And the reload kit has been ordered and confirmed and will be shipped to Less Than Resist. And that's all from us.
Thank you, Scott. Next up, we'll be having Brandon, our structures co-lead or structures lead, to talk about the projects that structure's been undertaking this year.
Hello, my name is Brandon. I am a sophomore mechanical engineering student this year, and I am the lead for structures. So just a quick overview before we get into the specifics. I'd like to talk about the major components that structure has been working on this year. So of course, the nose cone and airframes, which are G12 wound fiberglass, that we will be purchasing commercially. We actually have them in the lab ready right now for manufacturing. Next will be the avionics and payload couplers with a slightly new design. We're going to be focusing on a rail system rather than the more commonly used all-thread rod. Next will be the fin assembly, which thanks to Randy, we have a new kind of manufacturing method with the Nomex honeycomb and carbon fiber reinforcement. Next is the rail buttons, which are custom this year. They are 3D printed, resin 3D printed by a member of our hobby rocketry team. So a completely different kind of approach towards that from our previous years with Zenith. And lastly, the motor Hutchinson system, which is very similar to ours during zenith, which is a minimum diameter threaded rod retainer. So starting with payload, it is a 14-inch coupler. As I mentioned earlier, we are going with a rail system here. So there will be 4 3/8-inch fiberglass rails with helicoils on either end. One of the reasons why we are going towards a different system for our payload and avionics bays is because we've had trouble in the past with the assembly and overall just working with the all-thread rod system. So the rails will allow us to have very modular components inside. They'll be able to take different geometries, sizes, shapes. So it'll be much easier for assembly and designing purposes. The payload bay specifically will have a 1/2-inch bulkhead rather than the more smaller 3/16-inch bulkheads that we've used in the past. This is due to the connection point to our actual airframes. There will be 6 screws going radially through that bulkhead from the outside of our airframes. Some testing procedures that are applicable to the payload are the bulkhead compression testing, which is basically simulating the mass inside of the payload bay being accelerated during high acceleration events like recovery and landing. The avionics bay is a very similar design with our rail system. It's a 14-inch coupler again, but we have a few small differences. So we are going to have 1/4-inch bulkheads instead of the 1/2-inch, and there will not be any screws going into these bulkheads. Instead, we will have fasteners going through the outer airframe into the rails of this design. So yeah, this will be the point of fastener attachment to the airframe, nothing through the bulkheads. But of course, we will still have our fasteners going through the top face of the bulkhead, going into those rails, which will hold everything together. Some testing methods that we are trying to achieve this semester is the rail fastener testing. So those are, as I mentioned a second ago, the fasteners that are going through the top of our bulkhead into the rail. And I feel like it is necessary for me to mention that although we have not completed this testing yet, we do have pretty high hopes for the maximum strength of this assembly. But if in the end it does not meet our expectations, our second plan is to use aluminum rather than fiberglass, as it has been kind of recommended by a few of our alumni and mentors as well. A risk that we have seen with our bays and couplers is fastener hardware failure from excessive loading. We see this risk as high, and our mitigation approach is to ensure each load-bearing component has a minimum safety factor of 2 through our testing procedures that we should complete in the near future. And after mitigation, we expect it to be a low risk. Now our fin assembly. So in the past, I feel like Structures has been very keen on keeping everything as modular as we can get it. Basically trying to make every part replaceable if it needs to be in the event of it being damaged. We tried this approach for the PDR, did not turn out how we wanted to. So we went forward with a non-modular assembly approach of surface mounting fins on the outside of our airframe. So as I mentioned earlier, we are trying a new manufacturing method of honeycomb and a reinforcement of carbon fiber on the outside. With Randy's help, we are going to basically try our best to do this because it is a very new approach for at least me in this manufacturing. So hopefully we can do a good job with that. We are estimating a massive weight reduction of 81% from our previous designs of a solid core of carbon fiber. I believe each fin from Zenith weighed about 580 grams, which is a lot compared to the new method of honeycomb. Our major risk for the fins is fin failure from fin flutter and divergence. We calculated this risk to be a medium, and our mitigation is to follow the design method from Randy. And also, he has flight tested these fins on his own up to Mach 2.4. And in our appendix, we actually have some pictures of, I guess, those surviving a pretty hard landing. So if anyone wants to see that later, we can definitely take a look. But we've also used our FinSim value calculations to achieve a factor of safety of 2. And our risk after mitigation is low. Lastly, for today, the rail button assembly. So with Shasta, since we are going with a minimum diameter design, we won't be able to have any internal reinforcements as we did with Zenith. So our process is going to be surface mounting our rail button hardware on the outer diameter of our airframes with a weld nut, and we will put additional carbon fiber over that to ensure more strength. This creates a process for additional SRAD components in the future if we do want to go that direction. It could be smaller things like additional rail buttons or anything else in the rocket that we do see fit. Other components for this assembly is a number 1032 countersunk screw that will hold the resin 3D printed rail button to our airframe. And the rail button itself, as I mentioned earlier, is resin 3D printed from our friends in Hobby Rocketry. The major hazard that we see here is tear out of the rail button hardware during the exit off of the launch rail. And so before we actually start on the manufacturing of this system on Shasta's airframe, we'll be testing it to ensure that we have a safety factor of 2. And so after our mitigation, we expect the risk to be low. Thank you.
All right, and now for payload and their experiment.
Hi, I'm Isabel Naraidon. I'm a 4th year majoring in biology.
Hello, I'm Kevin Tran. I am a senior mechanical engineering student.
Please speak up.
Yes. I'm sorry. Hi, I'm Isabel Naraidon. I'm a 4th year majoring in biology.
My name is Kevin Tran. I'm a senior mechanical engineering student.
We are the co-leads of payload. So for our payload experiment this year, we're looking to review and observe fruit flies under the high stresses of launch before and after. We will be looking at things like oxygen intake, factors of metabolic behavior, instincts, before and after reflexes. And our hypothesis determines, our hypothesis is just to see if an induced state of torpor that can be achieved through therapeutic hypothermia will increase the viability of fruit flies in a high stress environment of launch. So as you can see on the right, our housing structure includes the FCCU, which is printed out of ABS. It'll house the control flies. Our PES, which is payload electronics section, will house all of our sensors. It is also printed out of ABS. And our bottom section is the Fly Experimental Containment Unit, our FECU. It houses the experimental flies that are under therapeutic hypothermia, and our cooling system that'll be insulated with aerogel. It is a steel container. So our overview for our model organism that we will be using is Drosophila melanogaster, which is just a fancy word for fruit flies. They share about 60% of their genetics with humans. It's modeled very closely to NASA's torpor-inducing habitats for the mission to Mars. Our control group is housed in our FCCU that'll undergo just the high stresses of launch on their own. Our experimental group undergoes therapeutic hypothermia in the FECU. We have completed our first round of testing, looking into therapeutic hypothermia under what rounds of times, how their behaviors are, how their metabolism is afterwards. And then we've also looked into IR sensing of our flies. Our biggest risk for this is overheating. Last year, we spent 6 hours in the queue. It can get up to 125 degrees in the rocket. This is our mitigations would be our cooling system. We've compromised between active and cooling system. We have a 2-phase system that Kevin will go into later in our presentation. And we also plan to follow proper procedure for cooling and handling of the flies.
So for the electronics for payload, this will be mainly for collecting data for the experiment. For our microcontroller, we'll be using the Adafruit Feather 32U4 ADA logger. And then we'll be using 2 different sensors for our data. One of them will be the Adafruit ACD30 for our CO2 temperature and humidity data. For the we're also using the Adafruit BMP 390 sensor for our pressure and altitude data. The reason we're using these two sensors is so that we can collect information and data on the environment that the flies will be in, and then using this data for our post-launch flight analysis. The testing we've completed so far is the Adafruit LTR 329 light sensor. We were going to use this sensor to monitor the flies to see if they were alive during the launch. But after testing, we've determined that it's not able to give us adequate data for our experiment. So we're no longer using this sensor. We also tested the SCD30 sensor just to make sure it works and to see how the data was outputted. And then it was able to give us good CO2 temperature and humidity data as we expected. The main risk for the electronics is having it overheat. The main cause for this would be improper placement of the electronics, having it too close together. The risk level for this would be high. And our main mitigation method will be proper placement of the electronics and making sure they're not too clumped up together, and especially with the battery. So after mitigation, we expect our risk to be medium. So to make sure our flies are at a cool temperature for the experiment, we are using a cooling system within our payload. The cooling system will be comprised of both an active and passive component. The active component will be only for the ground phase, so before the rocket launches. It will use a tube and pump cooling system that will continuously circulate cold water into the payload and around the vial to keep it at a cool temperature. And hopefully this will help keep everything cool while we wait in queue. Once we're ready to launch, we will disconnect the tubing from the connectors through an access panel that we'll have. And then we'll plug up the connectors to prevent any leakage of water, and then we'll be ready to launch. The passive component for the cooling system will be for maintaining a cool temperature using a cooling gel pack. Within the steel enclosure of the FECU, we will insulate it with aerogel, and this will help block out the high external temperatures while containing the cooler internal temperatures of the enclosure. For the testing we've completed so far, we were able to test the water pump and the tube configuration. This is mainly to make sure the pump works and that the connectors had no leakage. So far, we have not had any problems with leakage from the connectors, but we'll continuously test that to make sure no leakage happens. For our main risk for the cooling system will be the cooling system failure. The main causes of this will be the loss of power for the pumps, leakage, and high ambient temperatures. Our risk level is high, and our mitigation methods will be testing the tube connectors before assembling our payload, and then bringing backup power sources for our pump. And then after mitigation, we expect our risk to be medium. So we are currently working on programming our electronics so that we can collect the data from our sensors. We're also working on 3D printing the rest of our parts. If you look at the two pictures on the right, you can see the final printed FCCU. And then you can also see how the rails will fit into the notches on the side of the structure. We're also working on machining the steel housing for our FECU with the steel tube, as you can see in the left. For our planned test, we're going to do a lot of fly testing very soon. We'll be doing control and therapeutic hypothermia tests on the flies to see how the cooler temperatures affects the flies. And then we'll be using that data to compare with the other data we acquired during the launch of the rocket. We'll also be doing flight anesthesia testing to make sure the anesthesia works for the flies, to ensure that we can safely move the flies from one vial to another. And then we'll also be doing fly food testing. This is to make sure that the food we select for the flies don't trap the flies, and also doesn't grow mold easily to prevent any infections on the flies. And then finally, we'll be doing thermal oven testing to test our cooling system.
Perfect. Next up, we have recovery with Christian and Titus.
Good evening, guys. My name is Christian Rossi,
And I'm Titus Ventries.
and we're your recovery leads for Shasta this year. Right, so Shasta is very similar to Zenith last year. We're going to be using a single bay dual deployment configuration. To achieve airframe separation, we're going to be using a primary CO2 via the Raptor and a secondary black powder system. In order to ensure drogue deployment, we're going to have a lovely 36-inch chute, which has a descent rate of 105 feet per second and has a snatch force of 87 pounds. We might end up switching that over to a 12 or a 16-inch chute based upon some simulations in order to ensure our ground team's not walking upwards of 4 miles to the recovery site. For our main deployment, we're going to be using 2 L2 tender descenders connected in series. And we have a new series connection this year to show you guys. That's going to allow an 84-inch chute to be deployed. That descent rate is going to be 23 feet per second. It's going to have a snatch force of 162 pounds.
All right, so for our ejection system this year, we are using the CO2 as our primary ejection system, and we're using the Raptor. This uses a 24-gram cartridge in order to separate the nose cone from the rest of the rocket. We're using a black powder system for our secondary. We've used this in the past with both Zenith and Oberon, and this year we'll be using 2.25 grams with the separation force of 180 pounds. Main issue that we have, or the main hazard that we have with this is just complete failure, and this can be caused by improper wiring. And so our mitigation for this would be to ensure that we know how to properly wire the connections to the terminals. And so this year we're also using tender descenders. This is for the main deployments. Is 2 L2 tender descenders, and they're placed in series. Although the picture doesn't really, it looks like it is in parallel. The configuration of it is in series because it is you only need 1 out of 2 to work. So the tender descenders will be covered in a Nomex blanket to prevent any sort of fire hazard. And again, this has a very similar failure. Just improper wiring can cause it to not work.
For shot cords, the goal as far as safety goes was to go for 3 times the length of the airframe for all of our shot cords. We have 4 sections: the drogue, the main bag, the main, and the nose cone. For the drogue, the main bag, and the main, they're all going to use 1/2-inch 6,000-pound Kevlar. The nose cone is going to use a 1/4-inch 3,000-pound Kevlar. We're also going to employ a couple lengths of 1,500-pound tubular Kevlar on the tender descenders in order to keep them together during drogue deployment. For flaking, we were going to go for daisy chaining, but in order to pack everything in the nose cone and the body tube safely, and to give us some breathing room as far as packing goes during spaceport, we're going to be using flakes this time around, which also means we're going to be using rubber bands again. That's going to be able to absorb the shock of deployment. In order to ensure that the line around the bag ends up breaking, we're going to employ a length of shot cord that's going to be attached to a quick link on the U-bolt on one end, and around a quick link and the rubber bands on another around the main bag. We've conducted testing so far, and that's resulted in pretty successful tearing away the rubber bands, but we are going to conduct further testing in the future. And as far as shot cord failures go, cord failure and knot failure are all very, very common. It's really just due to improper tying of cords and improper selection of cords, and it can be mitigated by inspection and replacement of cords. Make sure you're not using any damaged cords, and to do your research on your knots and to test your knots to make sure they're going to be able to sustain the forces that you expect during flight. As far as parachutes go, so again, we're going to be using a 36-inch drogue chute and a 7-foot main. The descent rate for the drogue chute is going to be somewhere around 105 feet per second, and for the main, it's going to be about 22.6. Again, we might switch over to that 12 to 16-inch chute just in order to save us some walking room for the recovery team. We don't really want to walk that 4 to 6 miles. That would very much so suck. As far as hazards go, you have your burn damage, your shroud line damage. That's really just due to improper packing of your cords and improper packing of your fire blankets around your chutes. So as far as we adhere to proper packing procedures, we should be able to mitigate those risks and bring them down to medium and high respectively. And that is it for recovery. Thank you guys.
And lastly, avionics will be presenting their changes in order to ensure a nominal flight. Okay.
Hi, everyone. We're the avionics sub-team. My name is Samantha Tobias Leja. I am majoring in biomedical engineering.
My name is Aaron Wright. I am a senior in computer science.
My name is Orlando Rangel. I'm a freshman in electrical engineering.
Okay, so for avionics, we are in charge of the onboard flight system and our ground station as well. So here are the main goals of the avionics. We normally are in charge, of course, like I mentioned, the ground station and our coding process through that. Our main goals is electronic, what is that thing? Oh. Well, our electronics are in charge to deploy and recovery parachutes, collect data and flight transmit telemetry, and use the ground station to collect telemetry and track the rocket's location for recovery. And of course, fly an SRAD flight computer to record data and transmit telemetry. And we also go by COTS and SRAD, which is some of the overview from Space Board regulations. So, our ground station is, of course, our purpose is to receive telemetry from avionics system for GPS tracking and data. As you can see, there is a diagram there to explain our XP process and our ground station as well. This year, we're using a Yagi antenna, and we're doing our testing through NASA ham radio, and also with one of our members named Kurt.
So for the flight computers we'll be using this year, as we used previous year with Zenith, we'll decide to use the Altus telemetrum. It will serve as the primary flight computer, and its main function will be data logging and GPS tracking, and as well as perform dual deployment. We're going to be using it for 133 megahertz telemetry. That's going to help us, as we'll see later in the presentation, with our antennas. It also features a barometric sensor, high G accelerometer, GPS, and it's all going to be powered using a 3.7 LiPo powered battery. Of course, in terms of the risk, we determined that if anything happens, it's most likely going to be due to software bugs, glitch, or some sort of unintended behavior that we did not foresee in bug testing with our code base. And of course, the risk is high, and for mitigation, we will be of course, doing some more testing with regards to configuration, pressure testing. We're using our antennas and try to simulate as many flights as possible and try to get those fixed. And after mitigation, we see this as a medium risk because, again, things that are not foreseen will probably come back to haunt us. And for our redundant flight computer, we will be using an Easy Mini, as in terms of its data logging capabilities when compared to the telemetrum, it is practically identical. As again, it will be powered using another identical 3.7 LiPo powered battery. And in terms of risk, very similar to the telemetrum, any unintended consequences of the code base will come back to ensure that it will not perform its functions as we want it to. So again, we will be performing as many tests in the pressure chamber with our antennas to ensure that we do catch any unintended behaviors.
So I'm going to be introducing our SRAD flight computer to you. This is the third flight computer that avionics is going to be using. So the main purpose of this flight computer is for us at avionics to learn how to make our own printed circuit boards, or PCBs for short, and also make our own flight software and create a path for more advanced SRAD flight computers. So a really safe way to go about making our own PCB designs is to make a data logging flight computer. So the only job of this flight computer is to log data live in flight and transmit it with radio telemetry. So some of the sensors that are included in this flight computer are 2 3-axis gyroscope and accelerometers, a high G accelerometer, a 3-axis magnetometer, and a GPS receiver. So as you can see on the right, this flight computer uses 3 printed circuit boards stacked on top of each other with header pin connectors. We chose to use this design because it's really space efficient, and it's really space efficient compared to the vertically mounted board that we used last year. As for our risk, because this is our own flight computer, there might be modifications that are not reported or done outside of the specifications of the schematics. So this poses a really high risk because, well, a medium risk because any modifications can alter the functionality of our computer. However, this computer is not critical for the flight of the rocket, so we do not deem this as high of a risk. For our mitigation, we want to make procedures to track changes made in the flight computer, both in code and hardware, such as soldering. And after this, our risk is really low because while changes can be really damaging to the computer, they are really rare to happen after our mitigation. So for our antennas, we're gonna use these to communicate between the ground station and our flight computers. So we're using two Yagi antennas for the two separate frequency bands. So one of the Yagi antennas is going to communicate with the telemetron on the 433 megahertz band. And it's an antenna made by Arrow antenna. The second Yagi antenna is going to communicate with our SRAT flight computer in the 915 megahertz band. Risk that we identified with our antennas is that the Yagis are very directional. So we pose a risk of losing communication with the rocket if the antenna is not used properly. So we deem this as a really high risk because if we lose communication with the rocket temporarily, we also lose its positioning data through GPS and makes recovery much harder. Our mitigation for this is to inform the ground station users and the antenna users to properly use the antenna and practice aiming beforehand. Our choice for the Yagi antenna was because it has a bigger range than any other omnidirectional antenna, and because of that directionality and the narrow frequency bands, we pick up way less noise from the other radios around us and only focus on our own radios. So this is it for avionics. Thank you very much.
Cool. And lastly, we just wanted to end off the presentation with some final points. So this is our second attempt, as we all know, at a 30K solid propellant COTS rocket. We estimate that we're roughly 65% complete with our project, and our perhaps biggest barrier is funding. And we are estimating that we need roughly $5,500 for successful completion of this project. Next, for any alumni that are here, I know you've voiced an interest in attending Spaceport America Cup, especially those of you who were with the team when we weren't able to go to Las Cruces. So if you are interested in attending as an alumni, please talk to me afterwards and we can sort out some details. Also, lastly, I would really appreciate some feedback on our presentation style. I know it may seem like a race compared to the marathon that was in previous presentations. So anything positive or negative, we'd love to hear so we can further improve for further years.
And we just wanted to add the slide just to say thank you, show our gratitude to everyone who has helped us with knowledge, logistics, advice, financials, etc. So thank you to our team mentor, Andy. Thank you so much. Round of applause for Andy. Our alumni, Alex, Emily, Irvin, Carlos, Gustavo, Dom, Ozzy, thank you so much for all of your help in contributing with giving us feedback, helping us in terms of financial means, everything. So thank you so much, guys. And lastly, thank you to our professors, Dr. Hamami and Dr. Chain, for helping us as well as with feedback and helping us with providing a space for testing and things like that. So they're very helpful. So thank you so much, professors. All right, so before we start questions, we'll take a little break in case anyone needs to go to the restroom. And we also wanted to say happy birthday to Kevin. It's his birthday today, so we have a little surprise for you, Kevin, just because you came out and did some hard work today. We wanted to give you a little treat. Happy birthday.
All right, Kevin. In the pouring rain that was today, I ventured out and I got your favorite cake. This is an Earl Grey latte cake, that everyone wants to have. So had to drive through the traffic and rain and the pain that is I Kevin. But you know, this is a little small. There are a lot of people here. So what better gift to get him? His second favorite. This is the berry chantilly cake at Whole Foods, which is also open to everyone. So during your break time, I'll bring up the knife, and we have some paper plates and forks, and we welcome everyone to celebrate Kevin's birthday with us.
Do you mind if we sing you happy birthday? Do you mind if we sing you happy birthday? All right, you guys want to help join me? Happy birthday to you. Happy birthday to you. Happy birthday. Happy birthday to you. All right, you guys go to use the restroom. We'll come back to the questions in like what, 5-10 minutes?
Say, yeah, around 10 to 15 minutes, we'll be back.
It's. Right, I'm gonna come back tonight. No, let's give them 5 minutes. 5 minutes. 5 minutes to grab the food and take 5 minutes to get them. We done it like 8:45.
I was like, what do It's over there. No one's saying. Yeah, my friend. Actually, this is like an standard thing. Yeah. Yeah.
Yeah, you can.
Yeah.
Bye, guys.
I want to get it. Great job.
Some damage to your but let's take a look at the material. Tracking. That's something like, if that's here there, trying to get ready, like, you should have a. Yeah.
I'm okay. Still like coming down from the nerves, but doing okay. Not that long. PDR?
Yeah.
That's true. What are you guys gonna do?
I got a dog.
What kind of dog is
She's an Australian cattle dog. She's 7 months old. She's very smart.
Do you have pictures?
Yes.
Oh my God, please.
I personally love dogs. So she loves swimming. I think it's the dog part. And all she wanted to do was cuddle the humans. Like she would like be scared of like the regular dogs.
That's so cute.
I've learned.
She's Did you rescue her? Or is
Yeah,
she?
she's herself now.
Okay, her face feels like. How's the kid?
Look, just like cheating.
Is that good or bad? She's so small.
What did you?
She's a Australian cattle dog. Like it's like a more than 50 and make a dog.
She has a lot of energy, doesn't she?
Yeah.
Does she like tear up anything? Destroy anything?
She's definitely like kind of hyperactive, but she'll like attack shadows. So she's very gentle as far as going, but at the wall, she's like I've never seen a dog do that, but I think she's just like very interested. She needs like stimulation.
Oh, for sure. A lot of answers.
Yeah, it's a park.
Do you do any like puzzles with her? Any like brain games? Sure. Enjoy your cake.
Definitely puzzles. I'm still trying to figure it out.
Oh, so y'all just got her. Oh, okay, okay. Well, if y'all run into any behavioral issues, my partner's a trainer, so
Yeah, I'll definitely figure it out.
you guys get the SCR discount.
Downstairs.
It's amazing. And you've just got her in like a week and she's already doing it. It's really smart. Wow. Thanks for coming out. What did y'all think of the presentation? We started at 7:15, and we ended around 8:05. So I like to say it's pretty good. We went like 5 minutes.
Yeah, I walked around. Like I learned about my information that wasn't in class. So that I think there's definitely some stuff left out. But I balance. I think it's probably a better balance than what
Yeah, thank you, thank you. Yeah. After we got scolded by, I think it was Dr. Chang, she was like, the presentation, they're supposed to be much quicker. So we took that feedback into consideration and we really tried to apply it this time. I figured most people don't want to stay for like a 3-hour long presentation. Thank you.
I have my own hotel, so don't worry about that.
Okay.
I'll have my car. I might be I'll be there for you guys. Whatever you need.
That's awesome. Yeah, I know a couple of people have reached out to me asking, and Adrian, I don't know if he's reached out to you. He mentioned wanting to like go to Las Cruces.
Carlos, Carlos said it's still like.
Okay. Okay, understandable. We're so excited to have you. Yeah.
Everyone.
Thank you. I tried to go for like.
I couldn't find a shirt that I could. So I was like.
Yeah, no, it's like everything.
I didn't want to hear it said that. It is, it's so cool.
You're using.
It's like, where I give you like.
I missed it. Tried to sleep, yeah. Like I was about like our first.
Oh, you need.
I stopped like coughing. I was like, yeah, I just gotta get back. Like I can't leave it. I'm on antibiotics, but also nausea. I took an hour off because I was like, I need to look at this today. Yeah, no, for sure. I feel like if I didn't take it out, I would have just. Like a music video back in my head. It wasn't my best friend, but the people back there, they were asking what their life, and I was like, I was just like regurgitating the stuff that I like, where do you stay all the time? And I'm like, yes, genetic. I was like saying all the buzzwords, and Brandy was like, it's so really not at me. Like as I was talking about this, you eat. You were like, yes, validation. Yeah, I was like, I don't care how much I experiment wrong. That's what happened. I'm sorry.
Yeah, it's good.
You're like, yeah, it's good. You have to take a bite. And they're like, they'll be put in the trash.
That's we know.
What is that?
Not paper.
Yeah.
All right, guys, what should I even say? Like. All right, guys, it's question time. Time for those questions. Should I turn on the mic? All right, guys. It's question. Is it even on? No, it's off. I'm just gonna yell it.
Oh, there you go. No, never mind.
All right, guys, it's question time. Let's get ready to sit down and get those questions done. Question time. Question time.
You got it.
Wait, no, can you?
Hi, everyone. It's question time. Thank you, Izzy.
All right, so the next 30 minutes will be allotted to answer any and all questions that you guys might have. However, if we do not get to your question, we do have our email set in front of you, spacecityrocketry.uh@gmail.com. Feel free to send a question through there, and we'll try and answer as soon as we can. So who wants to start? Anyone have any questions? We have them all answered?
No, you're in the process of answering. I'm picking on.
Oh, I'm sorry.
No. I'm just being me. Just pick on each group, but structural environment and payload are all the list.
Haley, yes.
So my question is for Haley.
Okay.
I was wondering, y'all mentioned you're planning on doing testing for your cooling system. Ideally, what is the length of time, like what is considered successful in your testing?
Wait, sorry, would you mind coming up here and asking the question? Just so we can have it recorded.
I just yelled really loud.
Hey, if that works.
Okay. So my question is for the payload cooling system, I know y'all are gonna do validation for that, so I'm wondering what does success look like for that validation plan and kind of how does it stay cool before that point in time?
So for
Thank
a
you.
validation,
Yes.
so for our thermal oven testing, we'll probably be doing it in two separate parts. So one for the active, one for passive, and then like one combined. For the active component, we'll be seeing how long it can maintain the temperature we want. And then we'll use that time frame to readjust anything we need to. For the passive component, that will be to analyze like how long the internal temperature will stay at the range we want. Because I know with just the passive, it'll definitely like heat up over time. So that's like the main part for the passive one. And then combined, it'll just be combining both of the data sets that we want.
Yeah, so the passive, which is the steel enclosure that's insulated with aerogel, it'll have the cooling pack in it for whenever, it'll pretty much maintain it after the cooling system, the active cooling system is shut off. With the active cooling system, we will have ice water in the cooler and test that throughout time. Ideally at competition and after going through all of these heat chamber testing and thermal oven testing, if we decide or if we observe that the temperature is not maintained well enough with water and ice water itself, we do have additives. Like last year we had the ammonium nitrate that we added to water. And in the case that we observe no leaks for sure, we would be able to add ammonium nitrate and keep the water at a steady temperature.
How are you guys gonna have the cooling system in that space and the extra? Could you elaborate on it?
So he asked, how are we going to have the external cooling system at spaceport? Do you want to answer it?
Oh, maybe I'll do it. So we'll have like a cooler with like all the water and ice that we need for the pump and tube system. For the power source, we'll connect it to either a power generator or one of our cars. And everything else, no power.
Okay, just having been at spaceport a few times.
I have not been to space.
Yeah, I know you haven't. No,
Okay.
But just to elaborate, your cars are gonna be parked in a parking lot.
Okay.
And not near your tent. So whatever power sources you have, you need to have them at your canopy area.
Yeah, so in the
So-
case,
so-
in the case that because we can't have our cars there, I do have a portable battery that's about like this big that's used in case of power outages that I plan to bring. We'll hook that up to that. And then it'll be in our cooling reservoir that he talked about. The pump will pump water through it and back into the reservoir. We plan to carry that with us into the queue. We have a latch on the rocket or like an access panel that Brandon calls it. And it will, as we get the closest we can to launch, we will unplug the cooling system, seal that, and then screw in the access panel.
Okay, that brings up all my kids' engineering questions. Who has done a thermal load and calculation for the amount of heat you need to remove? I mean, you can use practical experiences but you need to put some, fingers to the keyboards and do some delta T calcs and specific heat capacities. And there's more BTUs in a pound of ice than there is in a pound of using nitrate. You don't have the environmental impact problems. You also can use dry ice, which will give you, it doesn't have as much CCP, but it gives you a lot more, it gives you a lot more cold. And so what is the temperature range you want to maintain inside your environmental system?
Our temperature range is 40 degrees Fahrenheit to 60 degrees Fahrenheit.
So you're going to be running anywhere from 70 to 80 degrees delta T between environmental temperature and inside your system. Are you using any kind of non-return quick connectors as you plug in, when you plug your system into your external cooling system?
What do you mean by that?
Okay, they make fittings like Swage Lock, Vortex, Warlock, a bunch of others, where you can just plug in and then unplug them, and then they're self-sealing, so that they keep whatever liquids in there is in there. You know, have you thought through how you're going to charge the system, get rid of all the air bubbles so you get good heat transfer, and then, you know, how fast do you need to flow the water through there? You may not need the water flowing through there with the aerogel installation as you think you might, but that's why you need to do some delta heat counts, some heat transfer counts.
Yeah, we're
Does that
definitely,
make sense?
yeah, that
Yes,
makes
sir.
sense.
Now, testing is going to be essential to verify the calculations and your assumptions along the way in making the calcs. You know that you got a 80-degree delta T, that's a pretty good heat loss. But it's good that you thought about it and you're doing it to protect your experiment. That's good. That's good work. A lot of good work. That's gone into this.
Thank you.
One last question on the expo.
Yeah.
How is the logistics of moving around like cooler little ice blood?
We haven't thought too much about it, but we could bring like a wagon or anything to carry the cooler. The cooler,
If you're dragging around the cooler, are you gonna have enough like black lines to also carry the rocket? What are you gonna have? I know this is such a great rocket.
well, for our tube length, the tube can be pretty long and still maintain a good speed for the water. So we're not too worried about the distance between the wagon and whatever is carrying the rocket.
Thank you. Thank you.
Any other questions?
Hey guys, can you hear me? Hello?
Hello, what's your question?
Hey, so good job on the presentation. I asked a lot of questions in the chat, but I think sort of just as an overall comment, I know everyone hates long meetings, but I feel like the CDR was sort of lacking some of the justifications behind y'all's decisions. So I know we want to have a 1 hour meeting and make it easy, but CDRs are sort of supposed to fully show us that the design is pretty close to being complete, if not already completed. And so these slides show us that you guys have done a lot of good work, but it doesn't show some of the detail or justifications, some of the things Randy touched on that make me fully know for sure that you guys, did all the analysis necessary, the calculations, basically everything required for the design process. And with 30 minutes of questions, I can ask you guys the questions I had in the chat, but it might take up the whole 30 minutes if we do that. So I might just email you these questions maybe, or
Yeah,
send it in the Discord.
We have a few note takers in person who have recorded all of your questions, but it will be good if you could email those to us as well, just so we don't miss out. And then we'll be sure to get back to you within a timely manner.
Okay, thanks.
Are y'all going to go through any of the chat questions right now?
I don't know. Chat questions.
Yeah. We can reserve the last 15 minutes. Unless anyone else has more questions. Yeah. We'll reserve the last 15 minutes for the online questions. So, and at like 8:45, if that's okay with you guys.
Okay, there's a lot of questions in here. So I think that would be challenging,
Okay.
but that's fine. I think a lot of it will probably have to be emailed,
Mhm.
but there might be some critical questions that we might want to hear answered here. So when we get to it.
Okay, for sure. Thank you. Okay, anyone have any more in-person questions before we start the online ones? Haley, yes.
So I have a question about the parachute packing. It wasn't really touched on all too much outside of the fact that we are still trying to do rubber bands, which is a little concerning to hear since that was our failure last year was rubber bands. What exactly are you doing to mitigate that risk? Only your no scale.
So the question was, what have we done to mitigate the risk of using the rubber bands again?
Also.
Yeah, just close it.
to Point out is during your testing, are you consistently putting the rubber bands in the same orientation, because that will impact the actual force to separate?
Oh, is it? Yeah, that's not supposed to be. No, it's not. I don't know why that text is like that. But anyways, we're gonna have a lanyard that's connected to a quick link that's connected to the rubber bands on the bag. And that lanyard would be connected to the bulkhead. So whenever the tender descenders break, the quick link that's attached will be able to pull on the rubber bands. So here we did testing to just get a proof of concept to show that, you know, this lanyard will actually pull on the rubber bands and take it off of the parachute bag. Yeah, and it's going to be part of future testing to kind of standardize the length and the placement and the tension of the rubber bands placed on the main bag and on the clicks as well. I know last year we had an idea going into spaceport. We changed that the more packing we did, and that ended up being very unbeneficial to the rocket. So yeah, it's definitely something we're going to prioritize in the upcoming weeks, and we're going to get down to a science. But that's pretty much what we've got so far.
Next question.
I have a team question. How as procedures will they that space for like how are those? You know, last year we struggled with language procedures and putting them to dial it. So very excited that people want to see it.
So the question was, how are the procedures going for Spaceport America Cup?
Yeah. Being completely honest and straightforward with you, we have not gotten started on those. We are aware that they are, one, required for the technical report, two, we need to get a start on them for the reasons you mentioned of not running into the same issues we did last year. Something that I've been thinking of to kind of change our approach from last year is starting earlier. I think being able to, I want to be able to talk to all of our sub teams and go with them through like an individualized plan of the checklist that we require, compare them to past years, see what we can do better, what we can do differently, and really get started and get a much better preparation for when we're at Spaceport. So, yes.
Yes, Emily.
I didn't have so much of a question as the question I had about this I addressed during our break with the team members. But I guess it's kind of a suggestion to the team. So with the philosophy of no longer focusing on modularity, you're increasing your risk that a failure is going to drown the entire rocket, right? A critical loss of one key component could drown the whole thing. So I was talking to Brandon about it and really just again, if there's a crack or a dent or something in that one thing can be had like as no go for flight. Or is it, you know, like, can you guys think about what you do for contingency contingency procedures if something is damaged or misplaced? Like, how can you address that? I didn't see that in your presentation, so I think before you need to be thinking about what happens when something goes wrong.
Okay. Thank you. So the comment was, we need to have a contingency plan in place, in case, something happens with the rocket, since there's, less modularity this year. So thank you, Emily. We'll definitely keep that in mind. All right, we have 3 more minutes left for in-person questions. Alex.
A question for Mr. Structured Man. But I noticed the way you're fastening the payload bay to the airplanes through the bulkheads, looking for the avionics space through the rails, right?
Yes.
I was just wondering, like, why is it different for the bays?
So, oh, yes. So the question was, why are we going for different securement methods for payload versus avionics space? So the main reason for the different attachment methods is to include larger screws for payload, since we are expecting a heavier mass of the components inside of there, around 8.8 pounds for the payload itself, and then additional for hardware, fiberglass components and everything else. So we were expecting a higher load during the high acceleration events such as landing. We were looking for getting larger screws in place for the payload component. And so that was the reason why we went the route with the larger bulkhead. So we could, have 6 of those radially through there. We have done screw calculators for each of those components for, again, the landing loads that we're expecting. And yeah, so due to the avionics bay having, of course, less mass, we required less thick screws, I guess, in diameter. And so we decided to take out mass of those bulkheads and then just go ahead and use the already existing rails to have 832 screws going in there. Okay. And I guess I should mention, since the screw sizes weren't specifically mentioned in the slides, for payload, there will be 6 1032s going into the bulkheads. And then for avionics, there will be currently 3 832s going into each rail. So 12 in total.
Thank you so much, Brandon. We have time. Oh, that's all the time we have for in-person questions. I'm so sorry. Let's try and get some online ones. Carlos, did you raise your hand? Do you have a question for us?
Yes, I do. Can you all hear me?
Yes, sir.
Okay, I hope it's not too loud. I know last year my headset was always super loud. First of all, really proud of you guys, like always. Great job. I do agree with the comment made before. I think that looking at the appendix, I can see that there's a lot of work and calculations that were actually done for all of this, but I think maybe for some of the really important calculations, it would have fit better in the slides. Maybe don't spend a lot of time on it, but at least reference it. But I just wanted to bring up this point real quick, and for recovery on, let me check my notes. Slide 34. The primary system is the CO2 system, and then the secondary system is the black powder. I think it would be better to have the primary ejection system be the black powder, just in case the CO2 powder doesn't separate the airframe, but it messes with the configuration of where all the components are. Maybe now your parachute is not protected by a fire blanket anymore, and then the black powder goes off, and you're kind of increasing your risk that the black powder could burn through your parachute. In case that happens, I think you're able to mitigate that risk better if you have the black powder system as your primary system. But I have other questions, but I'll just let somebody else ask other questions.
You can ask one question if you would like.
Okay, let me check my notes here. Oh, yes, the other major question I had here was, I know last year we had a separation or we used shear pins that added up to 120 pounds. I was curious as to why we're going with 180 pounds of for the shear pins this year.
Come up here. Answer.
So that's something we explained. Yeah. What's up, Carlos? So that's actually something we were talking about today with Brandon. Thinking about it, we're probably just going to stick with the 440 shear pins. I think did we do 3 last year? 3 last year?
Yes.
That worked perfectly well. Honestly, if it's not broke, don't fix it. That worked. Probably gonna continue going with that unless we find reason to go with some other configuration.
Okay. Okay. Yeah, sounds good. 2.25 grams of black powder sounds like a lot. I don't think we've ever used that before. So whenever you do your ground test, just make sure you're real careful. You know, considering what happened last year, I know we made some pretty big mistakes. So just be careful when you do your ground test and make sure that you practice your wiring, you practice your folding, you practice the assembly of the whole system. I think is very important. I think looking back at the lessons that we learned last year, just making sure that we are completely prepared to put our entire recovery system together. I think that's probably the most important thing about recovery.
Absolutely. And to touch on that a little more, we're definitely going to be adding shot cord to any nose cone ejection we do for ground testing. I think we've all learned our lessons as to what happens when we do not do that. In addition, we're also going to be starting quite lower with the black powder. So I think we're going to start from like 1.5 or 1.7 grams, just kind of incrementally work our way up to 2.25, just so we can see, what's safe. If we can go for a lower amount of black powder, obviously we can, and just kind of work that out and see, how does real life implementation work with the calculator.
Excellent. Thank you.
All right. Thank you, Carlos.
All right, Aldo, I see you have your hand raised. Do you have a question for us?
Hey, yeah, how's it going? So I kind of had a question regarding the PCB. I guess that's the SRAD flight computer sub team. When did you guys plan on having, or do you already have a prototype that you guys are able to test?
You guys want to come up and answer that? All right, he's coming. Thank you.
So we do not have a prototype yet for the PCB boards. However, we're planning on prototyping the individual components on breadboards.
All right, and do you guys have a manufacturer picked out? Do you guys know the lead times for that manufacturer and all that good stuff?
Yes, I personally have had experience ordering boards from JLC PCB. So we're planning on ordering the boards from them.
Also, we're
Alrighty, and then
asking alumni to just go ahead and triple check our PCB schematics. So we'll probably announce an announcement on the general chat. So whoever wants to come and join us, and we can have a Discord call to check our PCB schematics before we order them.
okay, cool. Yeah, that was actually another one of my questions is regarding the schematics. But yeah, the reason I bring it up is because you just want to make sure that sometimes, I know you can pay for like expedited shipping and all that, or if you don't pay for that, the lead times are a little bit unexpected. And it's kind of like, we'll get it out to you in anywhere from 1 week to 5 weeks, and kind of just planning ahead for that, because it's already April. And one of the things that I always used to tell people on my team when I was on avionics is that, we have these deadlines, but we always want to try to be ahead of schedule because you never know when delays that are out of our hands might happen. And if you kind of push that PCB, you know, these schematic reviews, or make sure that your DRC is clean and all that, then, you know, the more you delay, the closer you push to not, you know, maybe having your system on breadboards in a rocket because you couldn't get your PCB in time, you know, and that's something that, I mean, you can't, I don't even think you can have a breadboard on there. It has to be, you know, on a PCB. So that's something that you guys want to be careful. Well, that's something that you guys want to be careful with.
Yeah, we'll have to be careful about that.
Cool. And then what other questions that I have? Did you guys have anything else to make your guys' lives simpler once you have everything in hand? For example, is everything going to be pre-wired in the avionics bay when you load it in, or is that something that you're going to have to put together and then load onto the avionics tray and then load it into the rocket?
So because of the rail system that Structures has made, it's going to be really easy to integrate the avionics into the rocket. So once all the avionics are into the attached to the bulkheads, and then the avionics coupler is attached, it's all ready to go and can be integrated into the rocket.
Okay, and are you guys going to be putting that together on site? Like I'm talking about like the wiring, like the actual wiring. Are you guys going to be putting that together on site, or is that going to be put together ahead of time?
Ahead of time.
We haven't been planning for that, but how did we do that last year?
So for the whole wiring thing, we soldered everything beforehand, and we just went ahead and put it in one of the ground station boxes for it to travel safely. For the PCB ports, we were thinking of course ordering and soldering everything beforehand. And once we get to the launch site, we have a portable soldering pen, and we also have a portable charger for the soldering pen as well. If something does happen or something is loose, we also have backup as well.
Alrighty. And then, sorry, the questions just kind of keep popping up as we kind of discuss it. But and is Randy there? I don't know if is Randy there in person.
Randy is here.
Yeah, I'm here.
Okay, so he might know a little bit more about this than I do, but I remember there kind of being some regulations on what you could solder and what you had to crimp. Are you guys kind of aware of those differences there?
So on the computer, all the connections in between the boards, for the SRAM computer, it's all made through header pin connectors. That's how the boards are stuck onto each other. So there are no wires coming in and out of the SRAM flight computer other than the battery connectors.
Okay, alrighty.
And
Cool.
last year we had a fault with our spade terminals. So we're very aware now from our mistakes from last year. And our avionics members have also done research on the spaceport regulations and as well as the leads.
Awesome, cool.
Main
And then
the leads are if you put solder onto the multi-stranded wire,
Yeah.
it's more likely to fracture
Mhm.
than even using solid wire would be. And so that's why you have to use crimp. So instead of using spade connectors, your first choice would be ferrules, wire ferrules that are crimped on, and not a spade connector. Use and pick up terminal block that accepts a ferrule connector.
I have another follow-on question that maybe Randy will know, but I'm not sure. But is there a vibrational issue with using these header pin connectors?
People use them. A lot of the headers have fastening ears to lock them into place, but that has to be researched and tested on that to make certain that they are the locking type headers and not just the friction fit.
Gotcha.
And if it is friction fit, then you're going to have to come up with a mitigation plan to hold it in place, and bubble gum won't work.
On our SRAM PCBs, the headers are not, even though they are right now planned to be friction fit. What's actually keeping the boards together are gonna be standoffs. So on the sides of the headers, those black squares, there are holes where the standoffs will go through, and they will actually attach the PCBs to each other.
Sounds like a good plan. Just needs to be tested.
It needs to be tested. So
Thank you.
Testing and testing. So, yeah.
Thank you so much, guys.
Okay.
Thank you.
Cool.
Okay.
Yeah, yeah, thanks. And then just kind of one last comment. I guess I know you guys caught a lot of flack for kind of making the presentation really, really short. I was always one of those people that hated long meetings. Like you can ask Dom, Samar. I was always complaining because we had long meetings. So kind of if you guys can find a middle ground, I guess, between what they're saying, because it makes sense. I'm not going to say that they're wrong. It makes sense, you know, to have, I guess, support, to be able to support what you guys are saying, but maybe just have it in the slides and kind of not touch on it just to keep it short. Some middle ground. Cause I kind of like I said, I hated long meetings too. But yeah, you guys are doing an awesome job. And then avionics looking good over there.
Thank you, Aldo. Thank you so much.
Yep.
All right, we'll wrap up the last question with Michael Greer. Michael, do you have a question for us?
Yeah, I have two questions. The first one should be pretty quick. And that is there a cost breakdown for that big competition cost? I'm wondering what exactly goes into that.
Yes, we have a bill of materials. If you're interested, I can definitely send that to you. It's also in our Space City Rocketry drive. So if you go under admin, it will be there.
Yeah, in short, most of it is going to be housing, which we have put the initial deposit down for, but most of the cost is still there to be paid. They also raised the price to enter the competition with their rocket fees and Rocketeer fees. So most of the costs will come from housing and like just general competition fees.
Gotcha.
Gas. And gas, thank you.
transport, sorry.
And gas, yeah. Are y'all renting cars or something?
No, we're
Are you
taking our
driving
own
your own stuff?
cars.
Got it. Okay, yeah, my second question is more structures oriented. So I may have missed it because I know the structures guys were talking a few minutes ago, but I was really curious about the rails that have helicoils installed into them and how those are loaded.
Do you mean loaded as in like what loads we expect them to take?
Yeah, what's the load path through that structure?
Sure. So we're gonna pull up the avionics. Yeah. So with the avionics bay specifically, again, they have separate designs, but the current fiberglass rail will be epoxied to the inner diameter of the coupler. We don't expect there to be much loading between the rails themselves. We expect most of it to be applied through those screws, I guess horizontally through the airframe, to be passed through that into the airframe. So while the mass inside would create a force on the bottom bulkhead during landing and acceleration of launch, the force screws that are going vertically into those helicoils in the rails are calculated to handle those loads.
Yeah, so I'm not really so much worried about the screws themselves breaking. I'm confident that they're steel screws and that they're going to be able to take plenty of load. It's more about the helicoils into the fiberglass that I look at that and that kind of makes me a little worried. And so I noticed that there was a picture somewhere of the full rocket, and that might have been in an earlier slide, but I guess I noticed that I think it was the payload bay is between two sections of airframe. Is that correct?
Yes.
So looking at that, I feel like I see cases where those rails might actually be loaded. Maybe not so much during launch, but maybe during parachute shock events and things like that. And so can you elaborate a bit on that?
Sure.
Or
So
do you see what I mean?
I think I do, and correct me if I'm wrong, but to answer your first point, the helicoils in the G12 fiber or G10 fiberglass is an issue that has been presented before. We will test those to make sure that the tear out strength of those threads meet our expectations, but if they do not, we have plans to go forward with aluminum, which should more than likely meet those load requirements. I do see your point for the separation of two airframes for the payload bay. A majority of those forces from the analysis that we've done is going to be from the shock cords, the shock loading whenever the main parachute is released, and also just the simple gravitational weight of that during descent. I think the actual value for that force was set in recovery slides, but as of a few months ago is about 200 pounds. So we aren't expecting enough to tear out those helicoils. That there's 4 of them, of course, in those rails. I guess does that answer your question?
Yeah, what kind of tests are you planning on doing there? Are you gonna do like a tensile, like tear that screw out of the? Can you describe that a bit?
Yeah, exactly. So with Dr. Hamami in the MatSci lab, we've been planning to do it for a week or 2 in the past, but due to some specifics, we were unable to get the test completed. But yeah, exactly right. We're going to be doing tensile testing on a singular rail and screw with a helicoil inside, and basically just pulling those apart until failure to make sure that we know how strong that assembly is.
Okay, and then I hope that works out. Assuming, on, the off chance that it doesn't work, what's the turnaround time for turning those into aluminum rails?
Yeah, so actually at the same time, we're planning on testing the aluminum as well. Alex brought us a sample that we are going to test whenever we do the fiberglass as well. So we've held off on the purchase of the specific material for the rails in case something does go wrong, and in terms of that testing. So either way, we expect to have the same, I guess, plan for time, no matter which direction we turn.
Yeah, and we also ordered both the fiberglass rail and aluminum rod from McMaster, and they were arrived within a week.
Yeah,
so we're not too worried about having to order more of.
Okay. Yeah, I mean, y'all are running tight on time, so make sure you get those orders in sooner rather than later. That always tends to bite everyone in the ass. All right. Well, I really enjoyed the presentation. I think I have similar comments as Samar had. I think some of it felt a bit rushed, but I'll give my feedback either by email or in the Discord or something like that.
Thank you. Thank you so much.
Thank you.
Thank you.
All right, well, that concludes all of the time that we have for questions today, but thank you so much for showing up. We are very grateful. Thank you for all of the feedback, for all of the questions. We'll get back to you as soon as we can. If you did not get your question answered, please feel free to send it to our email. Right here, Space City Rocketry. Thank you so much, guys, and have a lovely day or lovely night. All right, can you check your recording?